Okay, so hello and welcome to this introduction to logarithms. The topic is logarithms, and so this is a very important topic and it is quite a lot. So we're going to break it down into 4 parts. We're going to talk about notation. These are the names and symbols associated with logarithms. We are going to talk about conversion from index form, to logarithmic form. Number 3, we are going to compute or solve logarithms. So we are going to compute logarithms. Here we are solving equations involving logarithms. And lastly, we're going to look at laws of logarithms, the rules, the principles behind logarithms. Okay, so I think we're going to start with equations that are called exponential equations. So let's quickly look at exponential equations. What are those? Exponential equations. So when you hear a term like exponential equations, the first thing that you have to do is break it down. So I hear exponential, I'm gonna break it down this way. You have to know that exponent means power. The word exponent means power. So exponent, I hear exponential and I'm thinking of exponent, and equation tells me that an equal sign is somehow involved in all this. So let's really look at this in more detail. So this is a typical, let me give you an example of an exponential equation. 3 to the power of x is equals to 81. 3 here is something that is called a base. X here is our exponent. 81 is our answer. So this should be easy enough. 3 is a base, x is an exponent, 81 is an answer here. So we can elaborate here by saying an exponent, another name for an exponent here is power or index. These are the ways that we can use interchangeably here, power or index. So by and large, when you're talking about an exponential equation, you're talking about something that looks like this. 3 to the power of x is equals to 81. What you have to understand here is that most of the time, usually here, most of the time, your unknown is the exponent. Your unknown is the exponent. So why am I going out of my way to explain what an exponential equation is? Because this is somewhat unfamiliar. The kind of equations that you are used to look like this. So you would normally have an equation that looks like this: 3x is equals to 81. This is just your run-of-the-mill, like normal linear equation where you have your unknown in a line with everything else, such that if I wanted to solve for x here, I would have to isolate x by dividing by 3 both sides. So in the end, I'm going to have x is equal to 27 as my answer. This should be easy enough. But here we are presented with a different problem altogether. 3 to the power of x is equals to 81. Suddenly, our unknown here is at the top. So how are we going to solve our exponential equation? You should take it as a fact that exponential equations are solved by expressing both sides in terms of the same base. I repeat, exponential equations are solved by expressing both sides in terms of the same base. We said 3 here is a base. Here we don't have a base because we don't have an index. This whole thing here is an index with a base and a power corner. So we're going to say 3 to the power of x is equals to, we're going to have to convert this 81 and in the end write this 81 with a base of 3 here. So we're going to have to write 3 here to the power of 4. 3 to the power of 4 is still 81. This is something that you know after like doing calculations with these. So 3 to the power of x is equals to 3 to the power of 4. And now we should really consider what the equal sign is saying here. The equal sign is saying whatever is on the left hand side is equals to whatever is on the right hand side. So far we have 3 being equated to another 3. So it should follow that x here is equals to 4. So this is true. So this is us saying 3 to the power 4 is equals to, well, 3 to the power 4. This is true. Now we can move on to logarithmic functions. There is a thing called a logarithmic function. What are we talking about when we say something is a logarithmic function? Remember, the topic is logarithms. So we needed to talk about something familiar before we talked about the actual logarithms, and this should be like your advice for anything else in life. If you want to learn something new, you should relate it to what you already know. In that way you can assimilate the new material and make it yours, but you always start from a place of relating it to what you know. So far we know about exponential equations. By now we know something called the exponential form. We know about something called the exponential form. We have to move to our new knowledge of logarithmic form. So how can we do this? So consider, this is how you generally write a logarithm, an equation in its exponential form. Y, our answer, is equals to a, our base, x here as our exponent. So in moving from the exponential form to the logarithmic form, we're going to say log base answer, log base answer equals to index. Log base answer equals to index. So let me just label everything here so you can appreciate everything. So answer here, base, and then we have an index here, a power. So you still have the ingredients this side, you still have your base, you still have your answer, you still have your index. So this is us starting from a place of familiarity, the exponential form, to something that is new, the logarithmic form. So let's make it concrete with a few examples. I'm going to start with an exponential equation. 81 is equals to 3 to the power of 4. This is the example from the last slide. So 81 is equals to 3 to the power of 4. On the other side here, this is in exponential form. Converting this to logarithmic form would mean we have to say log, what is the base? 3. What is the answer? 81. What is the index now? The index is 4 here. Log base answer equals to index. Let's do another one. 100 is equals to 10 to the power of 2. Once more, log base is 10, answer is 100, the whole thing is equals to 2. Okay, so at this point I kind of smuggled the symbols in there, the symbols that have to do with logarithms. So by now you're probably wondering what exactly log means here. So now we can talk about log notation. Let's talk about log notation. These are the symbols that are associated with logs. So far you have encountered log 10, log base 10. So log base 10 is equivalent to something called, just sometimes it's written like this, LG, like this. So log base 10 is sometimes written as LG. So there's a difference between these symbols. First of all, log base 10, this is universally accepted. This is very common. This is universally accepted. It is used in calculations, in engineering, it's in math, in physics. This is universally accepted. This is modern. This is relatively, compared to the other one, this is modern. Let's talk about LG here. LG is found in older literature. It is usually found in European. So this is not really a literature than a history lesson here, but it is found in European literature, in British and in German, and Russian literature. In German and Russian literature, it is used by those people in their math books. So what does it mean for us when we want to carry out calculations using these? So consider consider log base 10 here of 100. We have already established that this gives us a 2 here as an answer. So this means that we can rewrite, remember the equivalent of log base 10 here is LG. This means that we can rewrite this as LG 100. This is still going to give us a 2 like this. So I should add here that furthermore your calculator just has log written here. So if you wanted to find log base 10 of 100 is equals to 2, you're just going to punch this button here in your calculator. Log base 100 is equals to 2. In those instances in your calculator, the base 10 here is implied. It is not written, but it is implied. Base 10 is implied. So there's quite a lot, but let me try to do a recap here regarding notation. Notation has to do with the names and the symbols. So this is the symbol that you encountered first, the log base 10, and I'm saying this is used in many calculations. This is what we usually use in our calculations. So logarithms have wide application in engineering, in maths, and in science. And so occasionally you encounter a symbol such as this LG here. What you should know regarding this, so this is their history. This one is universally accepted. It is used in modern times, particularly like in the United States. This one happens to be found in European literature, in Germans and in Germany and in Russia. And in concrete terms now, regarding the actual math, log base 10 of 100 is equals to 2 is still the same as LG 100 is equals to 2. In your calculator, when you actually carry out the calculations using your calculator, you just punch log 100. The base 10 is implied. So that's what I'm saying regarding the notation there. Okay, so far we have talked about exponential equations. We have moved from exponential equations to logarithmic equations. We then talked for a while about logarithmic notation. Now we can see the conversion from logarithmic form back to exponential equations. So we have to realize that the reverse is true here. So we can move from logarithmic form back to exponential form. An example, log x here, log base x of 10 is equals to 4. This is going to give you, so what is our base here? Our base is x, so this is going to give you x here in exponential form. Log base answer, so answer is equals to 10, and what is your index is 4 here. Let's do another one. Say you had log base 3 of x is equals to 5. So in exponential form you would write it this way. What is your base? Your base is 3. And what is your answer? Your answer is x. And what is your index? Is here. Log base answer equals to index. So this was us moving from logarithmic form back to exponential form, saying the reverse is true. So now we have to look at the principles behind the logarithms, the rules of logarithms, or the laws of logarithms. Okay, so keep in mind what I said earlier about how you learn stuff. You always start with what is familiar and you gradually add the new material. So let's apply that principle here. We are talking about the laws of logarithms, and we have established that there's a relationship between indices or exponential equations and the logarithms. So it makes sense for us to talk about indices first. Before we can talk about the laws of logarithms, let's remind ourselves of the laws of indices. These are the general laws of indices. A to the power of m times a to the power of n is equals to a m plus n. Here we are saying when you are multiplying indices of the same base, you are going to keep the base and you're going to add the indices. A to the power of m times a to the power of n is equals to a m plus n. You are multiplying indices of the same base. You're going to keep that base and you're going to add the indices. This is easy enough. So what do we say when we are under the logarithms? So under logarithms, say you were adding log a here p plus log a here q. So this means that you are on this other side, you are going to multiply the logs, log a p q here. So there is that vague connection between logarithms and indices. This is what you know, this is what you are learning now, presumably. So when you are adding, there's an addition sign here, the operation is addition here. So when you are adding two logarithms of the same base, so let the record show that here you have the same bases, this base a, this base a. You are adding logarithms of the same base. You're going to keep that base and you're going to multiply the indices. So logarithms are the reverse of indices here. Let's make it concrete with an example. So say we had log base a 4 here, log base a of 4 plus log base a of 3. Our answer here on this other side is going to be log base a of 12. We are going to multiply 4 times 3 here. We're going to multiply 4 times 3 here. We're going to keep this base. We're going to keep this base. And we're going to multiply the logarithms here. I hope that's clear enough. Let's look at the second one. Once more, starting with what is familiar. Regarding the indices, we know that when we are dividing indices of the same base, you are going to keep that base and you're going to subtract the indices. When you are dividing indices of the same base a here, you're going to keep that base a here and you're going to subtract the powers. So let's look at the use case here regarding the logarithms. So we could have a logarithm like this. So log a p here minus log a q here. So this means that we're going to keep that base log a, we're going to keep the base and we're going to divide the indices. Now the reverse is true, we're going to divide the indices. Example, log a 12 minus log base a of 3 is going to give us log base a, and then we're going to have 12 over 3 here. All in all, we're going to have log base a of 4. This is our final answer. Let's move on to the next. So still regarding the laws of indices here, the third law of indices, it says when you have a power, this is our power that we are starting with, multiplied, then when you have a power raised to another power, you are going to, when you have a power raised to another power, you are going to multiply the powers. you're going to multiply the powers. When you have a power m here raised to another power, you are going to multiply the powers m times n. So let's look at the logarithms. So say here we start with log base a p here to the power of n. This is what is going to happen. This n here is going to come down here to the front, and in the end on the other side you're going to have n log a p and log base a of p. An example, log base a of 2 to the power of 3. We can simplify by bringing this 3 down to the front, and then in the end here same 3 log base a of 2. This is us simplifying based on the power rule. Let's look at one more example. Let's linking the indices and the logarithms. So we have a rule that says anything raised to the power of 0 is equals to 1, and we mean absolutely anything. So 10, I don't know, let's just string these zeros along. 10 to the power of 0 here is equals to 1. This is what it means. In indices, any number raised to 0 is equals to 1. So what do the logarithms have to say about this? So the logarithms say log base a here of 1 is equals to 0. In words, this says the logarithm of 1 is always 0. This is our answer here. The logarithm of 1 is always 0, like this. Finally, regarding the laws of indices here, it is implied that when you have a variable, a letter here, there is always a one here, such that it should come as no surprise that a to the power of 1 here is still a. So in logarithms here, log base a of a is equals to 1. Here we are saying the logarithm of the base. So you have base a and you are taking the logarithm of that base. So the logarithm of base is always 1. In concrete terms, log base 3 of 3 is equals to 1. You have a base 3 here and you are taking the logarithm of that base. Log base 3 of 3 is equals to 1. So a mini recap so far. We have introduced the topic logarithms by first talking about exponential equations. We showed what exponential equations are. We then went on to talk about exponential equations and linking them to logarithmic equations, logarithmic form to logarithmic form here. We have converted exponential equations here to logarithmic equations. And then what else did we do? We have talked about notation. We have talked about the symbols that are associated with logarithms. So far we've only covered log here, base 10, and lg, like this. And we have talked about their history here. And lastly, we talked about the rules. We also talked about the laws of logarithms. So we linked what we know about indices and introduced the laws of logarithms. So now we have to do some actual calculations using logarithmic equations. We have to compute logarithms. So pay attention to the word compute here. We have to solve, we have to find, we have to determine, we have to evaluate. So we are saying these are equations. In the end, when you are dealing with equations, the expectation is that in the end you're going to know the value. You are going to isolate your unknown so that you have it as it only, you only have your unknown as itself on on one side of the equal sign. So x is equals to something. In the end, you're going to find the value. You're going to solve. You're going to determine the value of your unknown. So equations are the opposite of equations are expressions. In expressions, usually they are associated with this language. So expressions are associated with this language. Both simplify and so simplify. Usually you just simplify expressions. You can't give an answer, you can't give a value, a number. So when you are dealing with expressions, they do not have an equal sign. You can only solve for these equations because they have an equal sign. So let's look at a few questions under computing logarithms. A typical question here might say, find log base 2 of 7. Find log base 2 of 7. There is no equal sign, but here's the trick. You have to understand that find here implies an equation. Find here means that this thing is an equation. So how are you going to do this? You're going to say log base 2 of 7 is equals to x. You're going to define your unknown here. So log base of 2 is equals to x. So how can you solve this thing? You're going to change it into its exponential form. So once more, this thing here is our base. This 7 here is our answer. This thing here is our index. Such that now we have in exponential form, we're going to have base 2 to the power of x is equals to 7. Log base answer is equals to index base answer index. Okay, so log 2 to the power of x is equals to 7. So usually this thing right here is an exponential equation. Usually you solve exponential equations by setting both sides to the same base. So remember, we had 3 to the power of 3 to the power of x earlier on. We had 3 to the power of x is equals to 81. In order to solve this exponential equation, we went ahead and said 3 to the power of x is equals to 3 to the power of 4. We ended up with same basis. Now we can't do that here. There's no way that we can write 7 here as a with 2 as its base. So there should be we should do something here. So we are going to convert this equation to logarithmic equation using logarithms of base 10. I repeat, we are going to convert this equation to logarithmic equation using logarithms of base 10. As it stands, we have 2 to the power of x is equals to 7. We can't solve it, it's insoluble. So we are going to introduce logs both sides. We're going to introduce logs both sides. Let's just write, my bad. Let's just write here, let me just do this. Let me start again, 2. Let me start again here. 2 to the power of x is equals to 7. It's insoluble because I can't rewrite the 7 here with 2 as its base. So I'm going to introduce logs both sides. LG here, LG here. What you have to understand about this LG here is that it has a base of 10. It has a base of 10. So what does this mean? So this means now that x now, so now these are logarithmic now this is a logarithmic equation. So x can come down here, and we're going to say x lg2 is equals to lg7 here. Our problem here in this exponential equation, originally our problem was that x was a power, our unknown was an exponent, and we couldn't solve the exponential equation because we couldn't change this number here to have a base of 2. What was our solution? And then we made this a logarithmic equation by adding lg, by attaching lg both sides, with the knowledge that lg here has a base of 10. So this is where we currently are. And then following the laws of logarithms, we took this x here and we put it at the front here like this. Now this is solvable. X is this thing is in a linear equation, such that we can, in order to isolate this x, we can divide both sides by lg2 here. So x all in all is lg7 here divided by lg2. Now you can punch this into your calculator, keeping in mind you can punch this in the calculator, keeping in mind that lg is equals to log base 10, and that your calculator just has log here. The base 10 is implied, so you can punch this into the calculator. This is going to give you 2.81, roughly 2.81. so this is where we are going to stop regarding the computation of logarithms. Okay, lastly, so far you have been looking at a system of logarithms called common logarithms. So far we've been dealing with a system of logarithms called common logarithms. Common because they are mostly used in engineering, in everyday math. So common because they are mostly used in engineering. There is another system of logarithms called natural logarithms. There is another system of logarithms called natural logs here. So natural logarithms, so where do we place them? Where do we situate them in math? So they are used in calculus. And so the notation associated with natural logarithms is ln here and e. We'll look at these in a later video, but what you should just know, your basic knowledge regarding the natural logarithms, is that the natural aspect of the natural logarithms, these logarithms arise naturally in nature. So these logarithms, they define things like population growth. These are natural processes. This is a field, this is a topic found in biology, which is largely a study of natural processes, also population growth. Here we could also have, say, radioactive decay. The natural found in the term natural logarithms means that we are looking at these logarithms describe processes that happen naturally, say population growth and radioactive decay, and we study this. So this is a domain. This is something that you find under the topic calculus. Calculus is a field of maths that was invented by Sir Isaac Newton. And the terminology, the language, the notation that you are going to use there is ln and e, like this. So we have reached the end of our introduction to logarithms. So note, emphasis on the word introduction here. There is a lot more that we can cover under logarithms. So this was a mere introduction to logarithms. So if you enjoy this style of teaching and you'd like personalized attention here with close monitoring and everything, if you want a personal tutor, that's what I'm saying, you can contact me on WhatsApp. So I'll link my contact and everything. So be sure to like and subscribe and look out for more content on this channel, and I'll see you on the next one.